kinematic indeterminacy is determined. Again, now to refresh your minds, kinematic indeterminacy is the actually the number of joint displacements in a structure. Joint displacements, again, now they can be translation or they can be rotations. The capability to move, freedom. And the displacement components are identified. So we look at the joints. If all the joints are not having the capability to move, it means the structure is kinematically determinate. But if there are certain joints which has the capability to move, then we count those numbers and that number is becoming the kinematic indeterminacy of the structure. A coordinate is designated to each independent displacement component. Now to each displacement component, what we do, we give it a label now, and we generalize this label. We usually give it in terms of the D, which is from displacement. So thus D1, D2, and D3, Dn are the redundant displacements at 1, 2, 3 up to n locations. If all the redundant displacements are restrained, the resultant structure is known as restraint structure or basic kinematic determinate structure, basic kinematically determinate structure. Now, if you remember, in flexibility method, we were looking for the statical indeterminacy. Now here we are looking for the kinematical indeterminacy. Statical indeterminacy was related to actions. And here now it is related to the displacements. There, if you remember, the unknown now actions, those were designated as ARs, and here the unknown displacements will be designated as Ds, which again from the displacements. Now, after identifying the unknown joint reactions, if you remember, we removed them and we got the release structure. Here, when we clamp these displacements, unknown displacements, the structure obtained will be known as restraint structure, which will be our kinematic determinant structure. Now, it first requires satisfying equilibrium equation. If you remember, there we were using the compatibility condition. Here we are using now the equilibrium equations for the structure. To do this, the unknown displacements are written in terms of the loads by using the load displacement relations. Then these equations are solved for the displacements. So unknown displacements are found by solving the equilibrium equations. Their compatibility equations conditions were solved and unknown reactions were known. And here now displacements will be known by solving the equilibrium equations. Once the displacements are obtained, the unknown loads are determined from the compatibility equations using the load displacement relations for n independent displacements. Now, the equilibrium equation will be AD1 is equal to ADL1 plus S11 times D1 plus S12 times D2 plus so on. And last we have S1n times Dn. And similarly, you can see the other simultaneous equations also. Now AD1, if you see, it is now the same we used to do in case of the flexibility method. It used to be DRS. This was displacement corresponding to redundant action. Displacement, if some precondition was given, so we used to record that value here, but it is now AD1, so it means here it will be action corresponding to the displaceable joint now, which is the unknown displacement. It will be the action, so we will be recording action if it is corresponding to the unknown joint displacement. So action we will be recording, so and that will be the precondition now in this case. ADL1, it used to be DRL, displacement in redundant corresponding to the loads. Here now it is action corresponding to the displaceable joint due to actual loads. Now action we will be calculating now when the structure, the basic, this kinematic determinant structure is under the actual loads now. The L is again for the loads now. So we will be now recording the action value. S11, it used to be F11, if you remember. There it was the flexibility coefficient. Here now it is the stiffness coefficient. D1, now it is taking the place of AR1 now. D1 is now, this is the unknown joint displacement. So now you can see the resemblance between the compatibility condition and this equilibrium condition. How these components will be calculated, we will discuss. But if you see the nomenclature of these equations, exactly it resembles to the nomenclature which we discussed in case of the flexibility method. Any question now till this point? This is a very important now discussion. And if you understand this resemblance, you should be very comfortable in solving the various structures with the help of this stiffness method. You can turn on your mics and you can ask me now. Is there any question? CR, are you there?
Yes, sir. Clear.
Clear? Acha, okay, so I'll proceed then. Acha, now we are writing these simultaneous equations in the matrix form. So writing the equations on the previous slide in matrix form called matrix formulation of stiffness method. So AD1, AD2 up to ADN you see. ADL1, ADL2 up to ADL1, then you see the square stiffness coefficient matrix and then multiplied by the unknown joint displacements now. So again, if you see the matrix, this notation, it corresponds to the flexibility method. Here AD, now this is the condensed form. Again, what is N? It is actually the degree of kinematical indeterminacy of the structure. So N cross 1. If you remember, DRS used to be the same thing. It was N cross 1. ADL, so this is now actions corresponding to the displaceable joints in the actual loaded structure now. So this is N times N. S is the stiffness coefficient matrix. N cross N depending on the kinematical indeterminacy, and it is again always it is going to be a square matrix. It will be positive definite and then it will be symmetric also times D N cross 1. How the stiffness matrix will be generated? If you remember, in flexibility method we were giving unit now action at the redundant locations and were calculating the displacements produced corresponding to the unknown these reactions. Here we will be giving unit now displacement and will be calculating now the actions produced. Right, so we'll discuss these things now in the coming slides. Now we can rearrange this now and get this D, the unknown joint displacements will become equal to S inverse times AD minus ADL. Again, if you see here, used to be AR, this used to be F inverse, this used to be DRS minus DRL. So again, you can find out the resemblance now in this one. Where AD, now let's define these various terms now, where AD is the external actions corresponding to the displacement joints. Right? This is the external action. At DRS, if you remember, that was the external displacement or pre-displacement corresponding to the redundant action. Here it is external action now corresponding to the redundant displacement now. AD. Next, ADL, it is actions corresponding to the displacement joints in the restraint structure due to applied loads. And fixed end actions, and for fixed end actions, for the normal cases, you need to memorize the values. I'll be showing you which one are the normal cases. Like let's say fixed ended beam where we have and it is loaded throughout by the UDL. That can be one standard case. Other can be we have fixed standard beam. At the middle we have pointed load, or pointed load, let's say it is off center, so we have relation for that one also. For the triangular now loaded beam, we can have, and partially UDL also, we can have a standard situation. D, this is the unknown joint displacements, and S, it is the stiffness coefficient, that is displacement per unit force. Now displacement produced by a unit force or action. So this should be the other way around, this stiffness coefficient. Faisal, are you there? Mr. Faisal?
Yes, sir.
Stiffness coefficient. So stiffness coefficient, displacement per unit force, that is flexibility. So we need to make this correction. This is the action produced by unit displacement. Action required to produce unit displacement. So we'll make this correction then. Now, stepwise solution procedure using stiffness method. The following steps must be followed while solving a structure using stiffness method. Step number 1 will be make the structure kinematically determinate by restraining the joints. That is, select the redundant joint displacements, construct the AD matrix. Now, once we make this restrained structure, we will label the unknown joint displacements, and corresponding to that, we will look into the structure if there are certain externally applied actions. If there are certain applied actions, that will become your AD matrix from the actions corresponding to the redundant joint displacement. So here, this is what we do. Second step, apply the actual external loads on the basic kinematically determinate structure and find the actions at the locations of redundant joints. That is, compute the fixed end actions. This will generate ADL matrix. So in second step, the ADL matrix is generated. Third step, apply the redundant joint displacement on the basic kinematic determinate structure. Now, to standardize the procedure, only a unit displacement is applied in the positive direction. This will generate stiffness coefficient matrix. So this will generate stiffness coefficient matrix. Unit displacement is provided corresponding to the redundant joint displacement, and then corresponding actions are calculated, and those actions will give you the stiffness coefficient matrix. Step number 4 now, equilibrium equation we need to apply. So apply equilibrium condition at the location of the redundant joint displacement to write equilibrium equations and solve for unknown joint displacement. So AD is equal to ADL plus S times T. RD is equal to S inverse times AD minus ADL. So unknown joint displacements are known now. After this, step number 5 is coming. Compute the member and actions like we did in the flexibility method. And step number 6 will be we draw the shear force and bending moment diagrams. Let's go through this example 1 now to illustrate the above mentioned procedure with the help of the general example. You are looking at beam AB now. It is fully loaded with UDL. At A, we have fixed support. At B, we have a roller support. Kinematic indeterminacy, if we ignore the axial effects, the kinematic indeterminacy of this problem is 1 degree, which is rotation at B. So kinematic indeterminacy, so one redundant joint displacement should be chosen, and that is rotation. Rotation we show with this arrow-headed curve. So this D, we designate this with the unknown displacement, which is theta B, actually rotation at B. So So step number 1 is selection of the redundant joint displacement. Rotation at B is taken as independent joint displacement. This you see. How we make it kinematically determinate now? We just fix this support, clamp it. So fixed support is provided here. So basic kinematically determinate structure or restraint structure is of this shape now. Always to restrain something, you will have to provide the fixed support, because fixed support is not allowing any horizontal translation, vertical translation, rotation. So this is now your basic kinematic, which is known as restraint structure now. And what we are restraining here theta B, which is rotation at B, and that is designated by D. Since we have this one joint displacement as unknown, so D, if you have multiple, then they start with the subscripts also, like D1, D2, D3, and D4, depending on the coordinates. Next now, if you see, if we put this structure under the load now, this is the basic determinate structure, the constraint structure now. And this constraint structure, when it is loaded, what will happen now? Here a moment will be generated, and that MB will be called as ADL. Whatever value now you get here, I can tell you now, I remember it when I was, let's say, in this, my engineering education, still I remember WL squared divided by 12. That will be the fixed ended beam for the moment, for this kind of situation. So MB, that will now, it is corresponding to the unknown joint displacement now, so that will give us our AL value. But realistically now, if you look at in the actual structure, if I ask you what is the moment here at B, straight away you will tell me as it is a roller support at the end, so it will be having zero moment now. But now when we clamp it, we are getting now this moment. We are getting this moment, which is violation of the whatever we have in the original problem. Now to put this MB in equilibrium, what we do, we rotate this in such a way so that the final moment here becomes equal to zero, which is in the actual kinematically indeterminate structure. And to standardize this, what we do, we provide a unit rotation and find out the corresponding action produced, that is known as stiffness. So because of this treatment, as we are now moment, so for moment we need to provide now rotation. Rotation is provided. And whatever end action we are going to get here, in this case, let's say this is small mb, so that will become our S now. And if we multiply this by the actual theta, which is our D actually in this case, that will give you, that will keep this MB in equilibrium. So in step number 3, when we come, we basic determinates this kinematically determinate structure. It is acted upon by unit value of redundant joint displacement. Here you see theta is equal to 1. Why we are not providing translation? The reason is that the moment produced corresponding to the unknown joint displacement, that was moment. The action produced was moment. So here now we need to put this moment in equilibrium, and for that case we will be providing theta now, not translation. And now computation of stiffness coefficient value. So the actions now will be calculated, and those actions will be giving us the stiffness coefficient value. Now ADL is known, S is known, this theta, which is D in this case, that is unknown. And from the previous slide, if you see, we have this here corresponding to this, the action that is ADL now, ADL, AD. AD here we can see no external action is provided here, so AD will become equal to 0. So now we can put them in equilibrium. So we apply equilibrium at the location of the redundant joint now, displacement, and solve the matrices to compute the values of unknown joint displacement. So from here now, if you see stiffness coefficient, from here it is known from step number 3. AD, from the very first step, it is known by observation or by slight calculations you can find out. ADL known from step number 2 now, so we can find out the unknown joint displacement. Once the unknown joint displacements are known, now it is kinematically determinate now, so we can solve it as we can find out the member and actions, and then we can draw the shear force and bending moment diagrams. Now you see a table here now, and we will be going again through the comparison now between flexibility and stiffness method. Comparison between the two, and you see the resemblance also in this. One is actually the resemblance in the steps I'm saying, otherwise one is just reverse opposite of the other one, reciprocal of the other one. Now, step number 1, determine the degree of statical indeterminacy. This is in case of the flexibility method. What we do in case of the stiffness method, determine the degree of kinematical indeterminacy. Choose the redundant actions here in flexibility method. Here, choose the redundant joint displacements. Now, to obtain the basic determinate statical structure, here the basic kinematic structure, and compute the DRS values here. DRS values here are, and here we find out the AD values. AD values are calculated in step number 1. Here you can see statical indeterminacy. Why? If you remember, we removed this AR. This was the redundant action declared. Here the redundant now joint displacement declared is theta 8b, rotation 8b, and it is designated by D. Assign coordinates to the chosen redundant. So 1, and this was also 1. Assign coordinates to the independent joint displacements. Next step now, we put them under the load. When we place this in case of the flexibility method, step 3 we are discussing, release structure is under the actual load now, and corresponding to the AR, this displacement was calculated, and it was given the name of DRL. This magnitude is placed under the actual loads, and corresponding to the unknown joint displacement, now the action is calculated, and that is known as ADL now. This is ADL action corresponding to the displaceable joint due to actual loads. So this is calculated. Next is the calculation of the coefficients now. This again on the left hand side, fourth step was what? We put this structure corresponding to the redundant action by a unit value, and we calculated the displacement, and that displacement was giving us the flexibility coefficient. This is step number 4, not 2. So what we will be doing here, we will compute the action at the coordinates in the restraint structure due to the unit redundant displacements now. What we do corresponding to unknown joint displacement now, we give a unit rotation, and we calculate the action produced now corresponding to the unknown joint displacement, and that is giving us the stiffness coefficient value. So this S will be calculated. Here F is calculated, here S is calculated. Here it was displacement, here it is action. Next, in this step number 5, let's say the comparison, here compatibility condition is applied in this flexibility method, while in stiffness method, the equilibrium condition will be applied. Hold on for a second. I got a call, so I'll be with you shortly. Okay. So now here, as I said, in step number 5, we use compatibility condition at the coordinates to determine the redundancy. AR were calculated, and here we apply the equilibrium conditions at the coordinate to determine the independent displacement. So here the unknown displacements are found by using the equilibrium condition. Step number 6 is the same compute member and actions, and here also we are computing the member and actions. We draw the shear force diagram and flexibility, so we draw the shear force and quantum movement diagrams in the stiffness method also. Now, example 2 now, compute the beam shown in figure below using stiffness method. Formulate the beam shown in figure below using stiffness method. So kinematic indeterminacy, if we ignore the axial effects now, we have rotation at B and we have rotation at C as unknown. So kinematic indeterminacy is 2 degrees. So 2 independent giant displacements should be chosen. 2 independent giant displacements should be chosen. Now selection of redundant giant displacements and assign coordinates at those locations. This is step number 1. Also compute AD values. Now, if you see, this is coordinate 1 now. At B, we have theta B actually unknown and theta C unknown. These two giants can rotate. So rotation, to make it generalized, now rotation at B, we designate this by D1, and rotation at C, we designate this by D2, and this D1 and D2 are becoming our unknowns. Now remember, again, the D1 and D2, these signs are arbitrary. You can take them clockwise, you can take them counterclockwise, and finally from calculations you will know which one are the correct signs. So D1 and D2, they are becoming our unknowns. Now AD1, AD2, do we see any now externally applied action here? If there is a rotation, let's say there is a moment now, and the moment is counterclockwise, let's say 5 kip feet, so our AD1 will become minus 5 kip feet. Why minus? Because D1 we assumed clockwise and that is in the counterclockwise. Corresponding to D2, let's say we have clockwise 10 kip feet, so this AD2 will become equal to 10 kip feet. Why positive? Because it is in the same direction of D2. So to make this AD1 matrix, we look at the externally applied now actions corresponding to the displaceable joints now. So here, these are equal to 0. So right in step number 1, we declare our unknowns and their corresponding externally applied actions. So rotation at B and C are taken as redundant giant displacements. Remember, you don't have any other choice to declare these redundant displacements. These are the only two joints. It's okay if you select this theta C as D1 and this theta B as D2. But these will be the two unknown joint displacements. Now to make this constraint structure, what we do, at B we provide a fixed support and at C we provide a fixed support. So these are the clamps now. This rotation at B is prevented and rotation at C is prevented. And this is now the basic kinematical determinate structure, which is the restraint structure. Now, step number 2, we will be calculating now the ADL matrix now. In ADL matrix, this restraint structure should be loaded with this P1 and P2, which are the actually applied loads. So here now you see restraint structure acted upon by the actual loads. Compute the values of actions in the restraint structure corresponding to the redundant locations. This will generate ADL matrix, so fixed end actions. Now ADL matrix, to calculate ADL matrix, this is fixed means you can now separate this, and remember from B, movement is not going to transfer now to BC. Similarly, from BC, movement is not going to transfer to BA. Fixed. It has the capability to resist whatever movement it is getting. Now, corresponding to D1, if you see, we will be having this movement clockwise. From this AB, we'll be having this clockwise movement, and it is in the direction of the assumed D1, so it will become positive. And then at the same location from BC span, we have this counterclockwise, so this will become negative. This algebraic sum of these two will give you the ADL value. Now, corresponding to D2, we have moment here, ADL2. So this, and it is in the same direction of D2, so this will become whatever moment is coming here, that will give you your ADL2 value. ADL1, again, you can see this is moment in the restraint structure under the actual loads corresponding to redundant joint displacement 1. And ADL2, it is moment in the restraint structure under the actual loads corresponding to the redundant joint displacement 2. Here now, to now generate the stiffness matrix, we go to step number 3 now. The primary structure acted upon by a unit value of D and computation of stiffness coefficient. This is the general statement now. Values in the basic kinematic determinate structure corresponding to the redundant giant displacement locations. It was 2 degrees kinematically indeterminate problem. So first what we do, we apply a unit rotation is applied at location 1. This was location 1, corresponding to coordinate 1, we apply a unit rotation and prevent it as at 2 as shown. And at 2 it is prevented. Here you see, still we keep the fixed support now. Only rotation, here you see this orange vertical line, it is becoming this inclined and theta is equal to 1. Rotation was unknown here, D1 was rotation, so corresponding to this theta 1 we are providing, and as a result this will become the deformed shape of this structure. Compute the values of S11 and S21. Now S11, again the subscripts, they are having the same meaning. First is the point of interest and second is where the displacement is applied. At one location the displacement is applied. Here at one location you see theta is equal to 1. So the second subscript is 1 and the first now subscript you can see 1 and 2. So look, this is coordinate 1 due to 1 and at coordinate 2 due to 1. Now, these relations we will be discussing how this 4EI theta at the near end when we give rotation moment distribution method, you should be recalling carryover factor and all these things. So here now, if you see, if rotation is provided at the near end, the moment produced there will be 4EI theta divided by L. We will prove this also in a while. And at the far end, it will become half of this moment and in the same direction. So 2EI theta or L you see. At the near end, 4EI theta or L. At the far end, 2EI or theta or L in the same direction. I'm explaining this BC span now. Here, this will cause unbalanced movement now. And how much is the unbalanced movement? 4EI theta or L plus 2EI theta or L. 6EI theta or L is the unbalanced moment. To balance this, we need to provide this couple now. So the unbalanced moment was in the clockwise direction. The balanced moment will be now in the counterclockwise direction. And its magnitude will be the unbalanced moment divided by the moment arm between this couple, which is L now. So here you see now 6EI theta divided by L square, and this is also 6EI theta divided by L square. And remember, this L is the BC span L. EI for the BC span, and theta is common as it is a rigid support and rigid member. So theta on the left will be equal to theta on the right because of the continuity. Left hand side, if you see, again, theta clockwise direction, so moment produced will be in the clockwise direction. 4EI theta, it is the near end, so 4EI theta divided by L, AB. At the far end, in the same clockwise direction, 2EI theta by L, half of this value. And this is the balancing couple now by the same concept, which we discussed for BC. So this is how, because of the rotation, the member end moments and the member end these shear forces are calculated. Now what will be S11 now? S11 will be the action produced corresponding to D1. So in this case, it is 4EI theta divided by L plus 4EI theta divided by L. Both are in the clockwise direction, so they are simply adding. And what will be S21? S21 will be corresponding to D2 now, add 2 due to 1, and that is 2EI theta divided by L, this action produced, which is 2EI theta divided by L. That easily now you can calculate. And remember, this is a standard now. When theta is given at the near end, it will be 4EI theta divided by L in the same direction, remember. Hold on for a second, let me please. Hello. وعلیکم السلام. خیر از کلاس کې ما خیر خو دی. نه زه خو کلاس کې ما زمان نن ګرانه ده ښه سبا به بیا. Okay. So now remember, once you know, look, theta is clockwise, and how this, now you need to make sure that you understand this deformed shape of this beam also. If on this deformed shape, if I draw a tangent here, if you are looking at this cursor now, this is, let's say this is a tangent on this deformed. So if you see here, look, this theta is clockwise. How we measure this theta? Starting from this initial position and touching the curve, this deformed shape. Now this is theta. This is how we finding out the direction. So this is clockwise, and here if you see, this is again clockwise. So theta, when it is given, it is not going to be this way now. Why? Because that will give you counterclockwise rotation. That is true for when counterclockwise rotation is given. Now, if theta is clockwise, so the actions produced will be also clockwise. The moments I am saying, as a result of this theta, the moments produced will be also clockwise. So at the near end, once we know that it is 4 ei theta over L, at the far end it will be half of this magnitude and it will be in the same direction. If it is clockwise, so far it will be also clockwise. Rest is simple now, mathematics, how we balance this couple now, so you can find out these support reactions. These actions you can find out very easily then. Any question till now? Now, the only point is we will have to prove this, how this 4 ei theta or L is coming. Is there any question? If there is a big pause, so I'll assume that I can go to the next slide now. Now, corresponding to a D1, this unit rotation was given. Now we need to give unit rotation corresponding to D2. So here now at D2 we are coming, which was this joint C. This vertical line, it is becoming this red horizontal because of giving this theta is equal to, we are releasing this support now to give it a unit rotation. And at 1 now, it is claimed. All the other locations will be claimed now. This was already claimed from the original problem. Now, as a result, now, what will happen? We again find out, because of this rotation, now we find out the member and actions produced. At the near end now, this is becoming our near end now, where this rotation is given. So this is 4 ei theta divided by LAC. At the far end, this will be the same clockwise, but half magnitude. So 2 ei theta divided by L, and this is the balancing couple now, 6 ei theta divided by L square, 6 ei theta divided by L square. This fixed support can totally take this moment produced now, and it is not going to be transferred towards BA span now. Now, calculation of the stiffness coefficients now. This is now stiffness at 1 due to 2 now, so it will become S12, and its magnitude will be 2 ei theta divided by L and plus 0. From BA, it is getting 0 now. And already now, if you see, S21, it was 2 ei theta over L, and here S12 is also 2 ei theta over L. So that is now the confirmation that this matrix is always going to be a symmetric matrix. Now here, this is a 2 due to 2 now, so S22 will become equal to 4 ei theta divided by L. This is corresponding to T2 now. These are our values of interest. So stiffness matrix is generated. After this, what we do? We go and write the equilibrium equation. So now here, instead of AR, if you remember from the flexibility coefficient matrix, it was AR is equal to F inverse times this was DRS minus DRL. So here now we have D is equal to S inverse times AD minus ADL. D is equal to S inverse times AD minus ADL. Step number 5 now, compute the member and actions, same procedure as discussed in flexibility method. So we compute the member and actions, and it will be the same now. One thing I'll be discussing now, how to grab the values now here. But here we can now discuss that. Member and actions now. Member and actions are the moments and shear at each point where it is going to be changed. We can find the member and actions using stiffness method when the redundant joint displacements are known. Let us illustrate now this one, that how we find out the this AM is equal to AM1, AM2, AM3 like this one, and then AML, AM. Now instead of AMR, we will be getting AMD now, and times instead of AR, we will be having D. So let us illustrate the procedure of finding member actions by stiffness method with the help of the above mentioned example. So this is the example now, and let's how we are finding out the member and actions now. You can see the externally applied load P1 and P2, A, B, C. These are the supports. It's kinematic indeterminacy. If we ignore the axial effects, it is 2 degrees. Theta C, theta B and theta C were the unknown joint displacements. Here now we declare that the joint rotations at B and C are taken as redundant joint displacement. So D1 and D2 you can see. Now to find out the member and actions, let's which one member and actions we are interested. So this is exactly the same procedure which we did in case of the flexibility method. Let's the shear at A is AM1, to the left of B shear is AM2, to the right it is AM3, and then at C it is AM4. Then moment AM5, AM6 and AM7 you can see their directions. These directions are arbitrary, but once you fix them, then this is becoming your reference. So AMs are, we are interested in these values, and these are our member and actions. Next now, AML. From where AML will be coming, this is the AML now, which is coming from the analysis of the restraint structure under the actual loads P1 and P2 you see. Here you will be having the member and actions, and the corresponding values will become your AML1, AML2, AML3, and AML4. Remember, it is exactly the same as in the flexibility method, but there it was coming from the analysis of the release structure, but here it is coming from the analysis of the restraint structure, and those member and actions now are becoming these values. Next now, stiffness matrix is generated, and that will be giving you the first column of the AMD matrix. Instead of AMR, we don't have redundant action, we have redundant displacement. So R is now replaced by the D now here. So now you see here, it is the same now restraint structure where unit rotation was given corresponding to D1, and we calculated the member and actions. And those corresponding member and actions now, those are becoming our elements of the AMD matrix. This will give you the first column. The last subscript you see, it is corresponding to when rotation is given corresponding to D1. So from here you will pick your AMDs now. This will now complete the first column of this AMD's matrix. Second column, when unit displacement is given corresponding to D2. So here corresponding to D2, this rotation was given. All the member and actions are calculated, and those member and actions will now constitute, that will give you the second column of the AMD matrix. After this now, when AMD values are calculated, D is already calculated, AML values already we know, so we can write this equation now. Instead of AM is equal to AML plus AMR times AR, now we have this equation. AM is equal to AML plus AMD times D plus AMD times this. These are the simultaneous equations. AML known, AMD is known, and D already known. So when we solve them, we get all the member and actions. And we will explain all these things now, how to pick these values, how to calculate the member and actions with the help of the examples. But you should be looking at the resemblance between the steps in these two methods. Now, this is now that how when we give rotation at an end, so the moment produced there will be in the same direction and it will be having a magnitude of 4 theta divided by L. At the far end, it will transfer by half of the magnitude and the same having the same direction. So 2 theta divided by L. And this is how the balancing couple is calculated. The total moment, total unbalanced moment divided by the moment arm between the couple. So 6 theta divided by L square. So conjugate beam method, if you apply, you can find this maybe taking 5 minutes. How it is done, we will discuss, but this is about the rotation now. When rotation is given at an end and the other end is fixed. You can draw this quickly. This is about the rotation. Now what if translation is given? What happens? When translation is given. Okay, after this now let's discuss this case where this translation is given. The A support now it is sliding down by delta A. So this settlement, let's say it is going through the settlement. Instead of rotation, it is going through the settlement. It settles down. So in this case, how the member and actions will be calculated. So if a unit translation is applied at A, then the moment induced in the members is shown in the figure, this figure. Now first, how to find out the direction of the moment produced at the near joint. Near joint means where the settlement is applied. Now this was the original and it is settling down to this position. So what will happen? It will try to go back to its position A. And when that is possible when it is applying this moment of clockwise direction. It is going in this direction, clockwise. And the magnitude of this it will be shifted to be in the counterclockwise direction and the balancing couple will be clockwise direction. This is how we fix its direction. Let's, instead of this A is fixed and let's this B is settling down. Let's to this position where RB is written, it is coming settling down here. So how we fix the direction? It will try to come back to its position, so its direction is becoming counterclockwise. Far and counterclockwise direction by the same amount 6EI delta B divided by L square. The balancing couple now, it was counterclockwise, so the balancing couple will become clockwise. So you can find out the direction of the couples also. So in case of now, when translation is given, the moment produced will be 6EI delta divided by L square. The couple produced will be 12EI delta divided by L cube. And how to find out the directions, we discussed that in very much detail now. Now to summarize, in case of the rotation given, the action produced at the near end will be in the same direction of rotation given. Magnitude will be 4EI theta divided by L. At the far end, it will be the same direction, but half of the magnitude. So it will become 2EI theta divided by L. The couple produced will be 6EI delta divided by L square, and it will be balancing the unbalanced moment due to the moments produced. In case of the translation, you know how to find out now the direction. Its magnitude of the moment at the near end will be 6EI delta divided by L square. At the far end, the same direction and same magnitude. And it will be balanced by the couple 12EI delta divided by L cube. And it will be the balancing couple now, means the direction will be opposite to that of the unbalanced applied moment. Now, after having this discussion, now let's prove the first one. This is going to be your task to prove this because of the translations, how these actions are generated. Now let's prove this, how this MA, we start from this now, MA is equal to 4EI theta A divided by L. How this action is generated when theta A is given at the near end. This is a beam now. At A, we will be giving now theta, so we have released this and we have converted this support to a hinge support. Far end is fixed now. It is a clockwise rotation is given, and let's assume now, this is assumption, MA, it is clockwise, MB, we give clockwise, and the support reactions, as these supports can give the vertical reactions also, so RA and RB in the real structure, these we have the support reactions. L and EI, you can have now these properties. Now rotation without transverse displacement of one end, this AVR, there is no translation, but only rotation is given. And the far end is fixed now. This is the situation. Now, to draw its bending moment diagram, we will be using the conjugate beam method now to find out the actions produced or to relate the thetas and these things. So MA, it is the support reaction here, the moment at support A, MA. What will be the moment here at B? It will be MA plus RA times L. So moment at this B now MB will be actually equal to MA plus RA times L. So that is drawn here. Bending moment diagram is becoming a trapezium. Why we are drawing it? Because we need to make a conjugate beam and load it with the M or EI diagram. EI is constant. So conjugate beam, we have a hinge support. So hinge is converting into hinge, and fix is now becoming a free, this support. Now we don't have any support here, free, fixed to free. And this is now loaded with the M or EI diagram from here now MA, and here it is MA plus RA times L. We divided this into a rectangle and into a triangle because we will be calculating the support reactions and the moments also. Now from equilibrium of conjugate beam, we have MA prime now, moment at A we are taking, and it should be equal to 0. Why? Because we have a hinge support at the end. So because of this rectangle, our moment will be becoming MA over EI, this one, MA over EI times L. So this is the equivalent now. This is the resultant of this rectangle. And how much is the moment arm? It will be L by 2. So this is clockwise moment M over EI times L by 2. Now let's do the same exercise for this triangle now. The resultant of this triangle will be half times, now this distance above this, it is RAL. So it will be half times RAL divided by EI and times L. This will become the resultant of this triangle. This will be the area of this triangle now. And how much will be the moment arm up to this? It will be 2/3 of the L. So here you can see 2/3 of the L. We are taking moment because of this rectangle and triangle about this A. And conjugate beam, these numbers are shown with prime now. So moment about A in the conjugate beam, this MA should be equal to 0, and this is how it is calculated. Now, we can put RA and MA from this equation in terms of one another. So RA, when we solve that equation, it is becoming minus 1.5 MA divided by L. And this is our equation 1 now. What will be reaction now in this conjugate beam reaction we are calculating. So it will be this MA over EI times L plus half of RAL times EI. So this it will be resisted here at A now, which is RA prime. So this is written here. This is the area of this triangle now. It is the area of the trapezium now. So MA over EI plus MA plus RAL over EI divided by 2. This is the average of these two verticals now multiplied by the distance between them. So RA prime now, RA already we know in terms of the MA now. So we put value here and RA prime is coming equal to MAL over EI. Now shear in conjugate beam, it is actually the slope in actual structure. Means theta at A in actual will be the shear in conjugate beam. Means this RA, which is, we can put this now for the actual structure, it will be showing you theta A actually. So instead of this, we are putting theta A now, and it is equal to MAL divided by 4 EI. Or if we rearrange this, so MA is equal to 4 EI theta A divided by L. And this is proved now. MA, now at the near end, moment produced will be 4 EI theta A divided by L. Now we can substitute this value here in equation number 1, and RA we are now calculating. So when we put these values, so RA is equal to minus 6 EI theta A divided by L square. Remember the couple we calculated? This is exactly the same. So minus means we need to reverse that direction. And its reaction at A will become 6 EI theta A divided by L square. Now from equilibrium, summation of upward forces, summation of downward forces should be equal, summation of Fy. So it is giving us now reaction at B now, 6 EI theta A divided by L. And similarly, we can take the moment at B now and can find out its value. So that is coming 2 EI theta A divided by L. So all the numbers are proved now. At the near end, 4 EI theta divided by L, far end 2 EI theta divided by L. Reaction at A and reaction at B also. You can do the same exercise now for when translation is given. So that 6 EI delta over L square, 6 EI delta over L square at the far end also in the same direction, and then the magnitude of the couple will be 12 EI delta divided by LQ. Now, fixed end actions for some general cases, you need to go back now to your engineering mechanics books and mechanics of solids books, and you can find out now these member and actions. Now, if we have a fixed-ended beam, and at L by 2, this pointed load at the middle of it is applied, so the member and actions produced will be PL divided by 8 and PL divided by 8. And these will be the vertical reaction. The member and moments you see, PL by 8, PL by 8, and this is P by 2, P by 2. This is, as I discussed this, L is the span, W fully loaded now. So the member and moments, WL squared divided by 12. And you can see the reactions WL by 2, WL divided by 2. Similarly here, if a couple is provided at certain distance A reaction at B, you can see. Let's fixed-ended beam, and with the triangular load now, maximum intensity at B, zero intensity at A now, so you can find out RA and RB by using this one. P, where P naught is the maximum intensity, and you can find out moment at A and moment at B. Now, if it is at off center now, the moment, let's say it is L by 3. Of L by 2, we have L by 3. So this is how the member and actions are calculated. Similarly here, if we have at the third point, the P loading, this is how the moments are calculated. And this is when the couple is applied at the met span, L by 2, L by 2, you can see how the member and moments and the support reactions are. These reactions are found. So you will have to memorize this instead of going and proving this. You should be, these values should be handy. It should be at the top of your head. Now, these are again the references like we are discussing in each session. So with this, I'll now take a pause and I welcome your questions. In case if you don't have any question, then what we do, we take a break, and then in next module, we will start now numerical problems, solution of the numerical problems by using this approach. Now, is there any question? You turn on your mics.
No, sir.
And no, Wasim is saying no. What about you, Mohammad Nadeem Khan?
No question, sir.
Now, are you feeling comfortable now because you have enough background of the flexibility method now? So how do you feel here now?
Feeling well, sir.
Yeah, you should be comfortable, and it will give you more comfort when we start now solving the actual problems, right? So now it is 12:20 now according to my clock, so you should be back by 12:40, right? We are taking 20 minutes break now. Okay?
Yes, sir.
So let's have a break. Okay. Let's start now module 6, and which is regarding analysis of kinematically indeterminate beams using stiffness method. So now you will see the application of this method to the analysis of beams. Now in this module topics to be covered are introduction, prerequisite for using stiffness method, stepwise procedure of stiffness method for beam analysis. We just discussed these things, but it will be a kind of, again, a revision. Analysis of beam 1, 2, and 3, and then you will get the assignments. Now, why beams are analyzed with the help of this stiffness method? One reason is that you can, those simultaneous equation, then you can write in matrix notation. When matrices are formed, very easily you can solve them with the available computers. And it is very systematic process. You can find out the support reaction. You can find out the internal resisting shear and bending moment at any section in the continuous beam. Now, prerequisites, again, you should be having enough concept of matrix algebra, must be able to find kinematic indeterminacy, and must know the formula and concept of fixed end actions. Stepwise solution procedure using stiffness method. Now, step number 1 is make the structure kinematically determinate by restraining the joints, that is, select the redundant joint displacements. Step number 2, we apply the actual external loads to the restrained structure. And we generate the ADL matrix on the release structure. And to standardize the procedure, we apply a unit displacement and generate the stiffness coefficient matrix. We calculate the member and actions corresponding to the displaceable joints, and the action produced by the unit displacement are the action required to produce a unit displacement, that is the stiffness coefficient. Then we apply the equilibrium condition at the location of the redundant joint displacements, write the equilibrium equation, and solve for the unknown joint displacement. So here you see the equation. The basic equation is AD is equal to ADL plus S times T, or D is equal to S inverse times AD minus ADL. And fifth step is compute the member and actions, and then is coming the real problem now. Now you take out your pens and notebooks and calculators, and let's solve this problem like we are doing it actually. So you will be running some calculations also. I'll be asking you. Everybody should be setting with. So quickly you draw this sketch now. We have a continuous beam, 2-span beam, support at A, fixed support at B, roller support, and C again a roller support. In the middle of this AB span, we have 30 kip load. Span of AB is 12 feet. Then at the mid of this location is not given, but it is looking like this is also in the middle. So we take it in the middle, 20 kip also. So BC, it is in the middle. If we take the total indeterminacy of the structure, it is actually 4 degrees kinematically indeterminate problem. What are those 4? One is horizontal translation at B, and then rotation at B. Then horizontal translation at C and rotation at C. But we will ignore the axial effects now. So it will become 2 degrees kinematically, and there will be theta rotation at B and theta, which is rotation at C. So kinematically indeterminate 2 degree, and we neglect. So neglecting the axial effects, if we neglect that is delta horizontal at B and delta horizontal at C, we are ignoring. So it will become kinematically 2 degrees indeterminate. So 2 redundant joint displacements should be chosen. EI is constant for this one. So now can I move, or still you are in the process of drawing this sketch? Can I move now to the
Yes, sir.
next?
Yes,
Okay.
sir.
Okay, I'm going to the next slide now. Can somebody tell me what will be the restraint structure for this one? इसके लिए restraint structure कौन सा होगा? What will be the restraint structure? Anybody who is clear that how we are going to make a basic kinematically determinate structure now?
Sir, we will make B and C fixed.
Very good. And what we will be stopping? We will be stopping rotation at B and rotation at C while doing that. Okay, so that's very good. So here now we identify rotation at B as D1 in clockwise direction and rotation at C as D2 in clockwise direction. And you can see in the rectangles A1 and 2 also, these are the now coordinates. At this location D1 and D2, we declare them as our unknown joint displacements. Corresponding to them, we don't see any externally applied action. No moment is applied at B, no moment is applied at C. So AD1, AD2, they are becoming equal to 0, 0. And then D1 and D2, we declare them unknown and unknown. So rotation at B and C are taken as redundant joint displacements. After this, we go to step number 2 now. Now, this is our basic, as one of the students said, that we will be fixing at B, providing a fixed support at B, and providing a fixed support at C. So this is our restraint structure now. After this, we move to step number 2 now, and we will be applying load now to this basic determinate structure. So you see here at B now we have a fixed support, and at C now we have a fixed support. You can bring them together also, this B joint, you can show it together also. But for convenience, it has been separated at this fixed joint into 2 fixed supports now. So here now, P1, P2, you see these are, but now we have actually applied loads at these locations. So 30 kip, and in BC span, it was 20 kip. Now here, if we apply this P1 L1 divided by 8, so 30 multiplied by how much was this distance? This distance is 12. So 30 times 12 divided by 8. Somebody should be verifying this value. 45. Is it coming 45?
45.
On the top? Yeah,
Yes,
okay,
sir.
40. So 45 and 45, as it is in the middle, so equal moments you can see. Similarly, reaction 30 divided by 2, 30 divided by 2, both are a fixed condition. And then it is in the middle, so 15, 15 kip. So member end actions for AB we found. Similarly for BC now 20 times 12 divided by 8. So it should be coming 30 and 30, and these are the direction. Top one is giving the stop sketch, it is giving the journal now, member end actions, and here we have specific to this problem. What will be ADL1 now? Somebody should be telling me. ADL1 कितना होगा हमारा?
5 kip.
5 तो नहीं होगा, 5 कहाँ से आएगा? How you calculate the
Sorry,
5?
25.
ना 20 ये देखे 25 होगा
20.
किस तरह आप कंपोनेंट्स वाइज मुझे आप बता दें 25 कहां से आएगा
सर ये 15 किप जो है ये पोजीशन 1 पे है और ये 10 भी है पोजीशन नंबर 1 पे है, तो इन दोनों को
नहीं
सम
लेकिन
करके हमारे पास
ये तो आपका ट्रांसलेशन आ रहा है ना ट्रांसलेशन अगर हो अगर फर्ज करें बी का ऊपर नीचे जा रहा हो सपोर्ट तो फिर आप 15 और 10 को लेंगे अभी तो आप रोटेशन ले रहे हैं D1 आपका अननोन रोटेशन था this is the reason that I am asking you intentionally more and more questions one to keep you awake and the other thing is so that you understand also अब क्या होगा what is now you tell me what will be ADL1 now the same student who was saying 15 plus 10 is equal to 25.
सर ये मोमेंट्स कंसीडर करेंगे क्योंकि उसके करिस्पॉन्डिंग है तो फिर 15 आएगा सर
ना तो आप मुझे कंपोनेंट्स में बताएं ना
ये 45 ये मोमेंट के फीट का एक मूवमेंट क्लॉकवाइज लग रहा है और 30 फीट टिप का एक एंटी क्लॉकवाइज मूवमेंट लग रहा है तो इनको सम करके हमारे पास 15 के फीट आएगा
so it will be plus 45 minus 30 which will be 15 and what will be ADL2
30 kip feet
very good ADL2 is here so this 30 it is in the same direction where the D2 direction right so plus sign and 30 is the magnitude so we go to the next slide and here you see now ADL1 how it is calculated 45 minus 30 is equal to 15 kip feet and ADL2 is equal to 30 kip feet so ADL is equal to ADL1 ADL2 15 and 30 are you with me now
yes
and you should be looking at this note also for rotation corresponding action is moment are you getting my point
yes sir
okay you don't get discouraged with this online system of teaching the reason is that nowadays everything is explained virtually now after let's say up to 3 years when you become the big consultants people will be sending you works from maybe from Australia, from UAE, and you will be explaining the things on this online system. So you should try to understand and try to understand the whole system and try to understand these lectures also. ADL1, ADL2, you know about the sign and you know about the magnitude also now, right? Okay, hai koi confusion abhi? Do you have any confusion?
no sir
Okay, now we go to the step number 3 now. So primary structure acted upon by a unit value of D and computation of stiffness coefficients which will be S values in the basic kinematic determinant structure corresponding to the redundant joint displacement locations. So first what we do, first a unit rotation is applied at location 1 and prevented at 2 as shown. Then we compute the values of S11 and S21 while doing this. Then a unit rotation at the redundant displacement location 2 is applied and prevented at 1 as shown and we compute the values of S12 and S22. So here let's see what is happening now. This was redundant location 1, this joint B. Theta is equal to 1 is applied. Here if you see or if you draw a tangent to this now deformed shape, so that will be also theta is equal to 1 and this theta will be also equal to 1. Member and actions 4EI theta or L2EI theta or LR. I explained these member and actions, so I'm not going to do it again now. Theta is equal to 1 is applied at corresponding to D1. At D2, it is clamped now and it was already clamped. These are all the member and actions. Let's see specific to our problem now. Theta is equal to 1. So here it is 4EI. Theta is 1 now. So multiplied by 1 divided by L. This L I'm saying now, the AB span. So this is becoming 4EI over 12. This is 2EI over 12. Now here the balancing couple 6EI over 12 square. This is that L square. For the right hand side, again, moment generated is clockwise. So 4EI over 12, this 12 is now this L, which is this 12. 2EI over 12, and this is the balancing couple. Now you should be very specific about finding out the direction of this couple and this couple. So 6EI over 12. Now you tell me what will be S11. Can somebody tell me what will be the value of S11? Why 0? Huh? You give me the reason now.
सर ये
Justify.
4 जो क्लॉकवाइज एंटी क्लॉकवाइज प्लस करेंगे सर तो 0 आएगा ना
तो
सर.
ये देखा बेटा, इसको आप देख लेना, दिस इज क्लॉकवाइज एंड दिस इज आल्सो क्लॉकवाइज, तो प्लस और प्लस को आप 0 कैसे कर रहे हैं?
सॉरी सर ये तो मैं गलत हो गया सर.
ये देखें, intentionally now I'm asking you such kind of questions so that you know how we fix the directions, और इसको algebraically हम sum किस तरह करते हैं. Clockwise, look, when it is clockwise rotation, so both action member and actions produced will be clockwise. So how we think about plus and minus then in that case? तो ये देखें 4EI और 12 ये होगा, प्लस 4EI और 12 ये हो जाएगा, तो 8EI और 12 हो जाएगा. And what will be S21? S21 क्या आएगा?
2EI
Sir,
divided.
Very good. This one,
Divided
which is the moment here, so 2EI, it is in the same clockwise direction, so 2EI over 12. आपका first column of the stiffness matrix generate होगी. और यहां से अगर आप देख लेना तो वही हम AMD के matrices यहां से हम generate करेंगे. This will be giving you. पहले वाले से क्या होगा? This one, अगर यहाँ पे आप देख लें तो आपके AML के values यहां से आएंगे. This will be giving you the AML values. ये आपको AML के values देगा. यहां से आपके क्या है? You will be getting the AMD first column values will be generated from here. तो आपका first column of the stiffness matrix is now complete. Now we apply to corresponding to D2 now a unit action. यहाँ ये देखें, where is this? Here. It is applied here. ये तो हो गया ना ऊपर वाला. अब now actually what is it? No, this is this one. So next now, why it is not here? It is here actually. ये देखें S11 is 4EI over 12 plus 4EI over 12 तो 8EI over 12 हो गया, और S21 is 2EI over 12 तो 2EI over, तो फर्स्ट कॉलम आपका जनरेट हो गया. सेकंड के लिए हम क्या करते हैं? वी अप्लाई नाउ करस्पॉन्डिंग टू D2 अ यूनिट रोटेशन उसी डायरेक्शन क्लॉकवाइज में प्रोवाइड कर रहे हैं. दिस विल बी द रिफ्लेक्टेड शेप. ये देखा अगर ये क्लॉकवाइज जा रहा है तो इसका टेंजेंट भी क्लॉकवाइज जाएगा. दिस इज द पॉसिबिलिटी. यहां से आप स्टार्ट लेंगे, दिस इज योर 0 एंड टचिंग नाउ द डिफॉर्म शेप नाउ व्हिच इज आल्सो क्लॉकवाइज. अगर आप कहते हैं कि नो इट इज गोइंग टू बी दिस वे, तो यहां पे आप टेंजेंट करेंगे, सो दिस इज काउंटर क्लॉकवाइज व्हिच इज नॉट पॉसिबल. Clockwise rotation will be clockwise rotation and clockwise actions will be generated. Near end पे 4EI theta और L हो गया, far end पे 2EI theta और L, and this is the balancing couple now. Now you tell me what will be S12? S12 क्या होगा?
सर 2EI divided by 12
2EI और थीटा हो गया, 2EI और 12 हो गया, और यहाँ से लेफ्ट साइड से क्या आ रहा है? 0 आ रहा है. सो
जी सर.
दिस इज 2EI और क्लॉकवाइज में, सो दिस इज 2EI और S22 कितना हो जाएगा? दिस इज योर S22 ना 4EI दिस थीटा तो आपका वैसे भी 1 है, सो वी डोंट राइट इट हियर नाउ. सो 4EI और 12 हो गया. The stiffness coefficient matrix is complete now. और यहाँ से आपका AMD का सेकंड कॉलम जो है ना वो आपका कंप्लीट हो जाएगा. ये आपका वर्टिकल रिएक्शन अगर ले रहे हैं तो 0 आएगा, ये वर्टिकल रिएक्शन आपका 0 आएगा. यहाँ पे ये वैल्यू आप लगाएंगे, ये वैल्यू. सो we'll discuss this when we get there. Next now, this is now S12 which is 2EI over 12 and S22 4EI over 12 हो गया. So now this is your complete stiffness coefficient matrix. EI we take it common. Then within parentheses, now you can see, you can take out 12 also common, EI over 12. So you are left with 8, 2, 2, 4. This is your stiffness coefficient matrix. Now it is easy to write the equilibrium equation and solve this. So this is the equilibrium equation now. And here we put the values as inverse. So 12 we took out common. EI over 12, so inverse is 12 over EI, and here we take inverse of this. AD1, AD2, we were not having any corresponding actions, so 0, 0. ADL1 was 15 and this was 30. So D1 and D2 are coming equal to 0 and minus 19. Negative sign shows that our assumed sign displacement is in the wrong direction. Yeah, okay. After this now, we go and we are finding out the support reactions now. These are the member end actions, S1. Now you see vertical at this. This is just to show you at BF, you see the vertical reaction is S1. Quickly now you mark this. At B, the vertical reaction is S1. At C, it is S2. And at A, it is AS3 now. And our equation will be now, instead of AM, we write AS is equal to ASL plus ASD times T. Support reactions we are finding, not the member end actions. So we replace the M in the equation by the S. Have you drawn now this quickly? AS1, AS2 and AS3, where they are located? Can I move to the next slide?
Yes, sir.
Okay. Now, this is my next slide. Now you see here, ASL1 corresponding to this B now, whatever support reactions are coming, that will become my ASL1. This is ASL2 at C, and at A, it is ASL3. From the same location. Now you see the numbering, it is corresponding to AS1 now, AS1, AS2 and AS3. Now ASL1, it is the summation of these now shears now, which will become 15 plus 10. This is the total reaction showing this ASL1. So ASL1 is 25, ASL2, I'm not finding the shear now, I'm finding the total support reaction. ASL2, it is 10, and ASL3, it is now 15. From where these are coming, this is the the strand structure under the actual loads. You see this 30 kip and 20 kip. And if you want to find out the AML values, you can find out the AML values from here also, but we'll discuss those one also. But if you are interested in the support reaction, you can directly find them out. Next now, the ASD values, here it will become ASD11, ASD21 and ASD31. So now can somebody tell me what will be the value of ASD11?
Zero.
Very good. This is now plus 6 EI or this is minus 6 EI over 12 square. So this is 0. This is 6 EI over 12 square and this is minus 6 EI over 12 square. So first column, that quickly you can complete. And from where these values are coming, this is the same from where we generated the S11 and S21, where the theta was applied corresponding to D1. For second column now, this is now when rotation is provided corresponding to D2. Now S1 ASD12 will become minus 6 EI over 12 square. This is plus 6 EI over 12 square and this one is 0. So here now you see all those are simplified and we see these values. This is, you see that 0 from the middle B when up and downward was cancelling each other. Now we put these values and directly we get the support reaction. This was the ASL, these are ASDs and these are the Ds now. So support reactions directly we found. You can check them now upward and downward. So downward 50 and upward should be also equal to 50. support reactions are found. We are interested now in the shear and moments. And we use our conventional now, AM is equal to AML plus AMD times D. So quickly you draw these references now. Where is your AM 1, 2, 3, 4, 5, and 6? Now it's looking like stupid now, AM 6 and AM 7. They should be equal and opposite in. But let's prove it that we are getting this situation. AM6 must be equal to AM7 now in order to have this continuity. And they should be in the opposite direction. But let's see what we are getting from the calculations. So AM1 FUC already we calculated them, but let's prove this by this method. AM4 already we calculated. This is now, if we add this AM2 and AM3, it should be giving you the AS1 we calculated at this location. Now, from here, this is now when it was under the actual loads now, the basic kinematic structure. Now, as AML1 is 15, AML2 is 15, AML3 is 10, AML4 is 10, AML5 is minus 45, AML6 is 45, and AML7 is minus 30. So this gives us now this, you see here, all these values are recorded here. Now AMD values, so here now when theta was applied corresponding to D1, all these member and actions were calculated. AMD 11 will be minus 6EI over 12 square. This AMD 21, it is 6EI over 12 square. AMD 31 minus 6EI over 12 square. AMD 41, it is 6EI, here 2EI over 12. Here 6EI, it is in the positive, so 4EI. And then we have MD7 one, it is 4EI over 12. So we can pick the corresponding values from here and it will complete the first column of the AMD matrix. Similarly, to complete the second column, we need to provide a unit rotation corresponding to D2, find out all these member and actions and record it. Here AMD21 is 0, AMD22 0, AMD32 it is minus 6EI over 12 square. 4 to 6EI over 12 square. Here AMD51 it is 0, AMD6 to 0, and AMD7 to it is 2EI over 12. So this way now we complete this one. After completion of this AMD matrix, now we run the matrix calculations by using this equation. AM is equal to AML plus AMD times D. Here all the values now we have, we run these numbers and here we get now the final. You see the same 15. Here we consider this as a shear, which is the support reaction at A actually. Then AM to AM3, if you add them up, we get the same 28.75, which was the support reaction. Then at C, 6.24, this is exactly the same support reaction we got here, AS2 if you remember. This is minus 45, means we need to reverse this direction. Initially, we assumed this AM5 in the clockwise direction, but because of this, it is now becoming counterclockwise. This one is positive AM6, so we put them in the clockwise, but this one is coming negative. Now you see here, they must be balancing each other at this support, so we reverse this direction. This is completely analyzed structure now. After this, what we can do, we can draw the shear force and bending moment diagram, which is the regular business. Pointed load. So 15, it was the shear here. It is constant because we don't have any load. Because of this 30, it is coming to minus 15 now. Again, no load, so constant. Because of this now, this 15 is here to the now 13, it is coming to 13.75. Again, no loads, constant. And because 6 point, so it is coming here now. This is now the complete shear force diagram. Bending moment, we calculated this 45, tension, causing tension in the outermost fiber. So we are drawing this below the 0. Now again, tension in the topmost fiber, so 45. Here you can calculate this. This will become 45 minus 15 times 6. So plus 45, Similarly, you can calculate this one also. It is 6.247 multiplied by this 6. So you must be getting this one. So this is regular business rest. Once you know the support reactions, the member and actions, you should be able to draw the shear force and bending moment diagram while looking at the externally applied loads and the member and actions found. You should be able to do it. And look, this is important. It should be roughly to the scale. I don't want to see this 13 higher than this 15 now. Roughly, if you see, it is showing to the scale. 15, it is the same 15, 13, it is a little bit less than this 15. 6 points, so it is almost half of this value. Similarly here, 45, 45, 45, the same scale you see. 37, it is a little bit lower than this 45, so it is looking. It was fixed support, so here we have a moment. It is a roller support, so here at the end roller support, so here we see zero bending moment. Now with this we complete problem number 1 now, where you saw how we declare the kinematic indeterminacy of the problem, how we chose our redundant joint displacements, corresponding to them, how we make AD matrix, then how we calculate this ADL matrix when we put this restraint structure under the actual load out the corresponding member and actions, how the stiffness coefficient values are calculated and stiffness matrix is generated, how the equilibrium equation is written, how that is solved for the unknown joint displacements, then how we find out the unknown support reactions, the unknown member and actions, and after knowing all these external and internal member and actions, how we draw the shear force and bending moment diagrams. Now remember, when I'm explaining these things, each and everything will be fresh in your mind. So when we finish this class, you go and rethink, because your mind is hot now. So you reproduce whatever I'm saying. And then you verify all these things with my lecture also, and then you start solving this, review this particular problem, and then start solving other problems. And what can be the good option? The good option can be you verify whatever you solve on flexibility method. You just verify the solution of those problems by using the stiffness method. So now you are getting an opportunity to verify your values by using the other method also. Now with this, now you can turn on your mics and you can start asking me questions. Now, shall I go now to the next problem, which is this one? Problem number 2. Or should we now, if you don't have any question, we have 2 options now, either to continue problem number 2, or if you want to go and review and prepare this and may come in the next lecture and start asking me questions. And then we can complete this beam analysis by the stiffness method.
Yes sir, इस तरह ठीक है सर.
इस तरह कर लेते हैं. अच्छा ठीक है. अच्छा, so what we do now, let me stop the recording now first. Okay. "34 students I can see now, which are joining the class. Are you comfortable now?"
Yes sir.
सर जी फिर इस मैकेनिकल का नेक्स्ट क्लास में ओवरव्यू भी दे दीजिएगा.
नहीं क्या करूं नेक्स्ट क्लास में मिस्टर एमल?
सर इसको हम सॉल्व कर लेंगे, इस क्वेश्चन को, क्वेश्चन नंबर 2 को, जो प्रॉब्लम 2 है।
ना एहतशाम, इस तरह है ना कि अभी आप मतलब अगर आप 60% भी आप समझ रहे हैं ना, सो यू आर इन द कंफर्टेबल जोन एंड इट इज वेरी मतलब सेटिस्फैक्टरी सिचुएशन। लेकिन अगर आप बिल्कुल भी नहीं समझ रहे ना, देन समथिंग इज, इट इज वेरी डेंजरस, लेट मी टेल यू दैट वे। हाँ
यस सर, समझ रहे हैं।
समझ रहे ना, अगर 60% तक आप, बाकी आप ग्रुप डिस्कशन करके आप खुद ही मतलब दूसरे एग्जांपल्स करके ना, everything will be coming now from practice. When you start practicing it, 100 questions will be coming, they will be popping in your mind. ये आप याद रखें कि सिर्फ मुझे मतलब है, आप इस तरह नहीं आप इसको समझ सकते कि just like let's say a movie, you are just watching it, my lecture. No, unless and until you put your pen on your page and start writing each and every step, that is the ideal condition to learn something, especially these mathematical problems. So ठीक हो गया. We now finish this class here at this stage, and inshallah next week is going to be the 7th session. और उसके बाद आपका मिड टर्म होगा.
यस सर.
अच्छा ठीक है, तो आप मिड टर्म के लिए भी साथ साथ आप तैयारी शुरू कर लें. If it is online mid term, so you must expect some tricky and difficult problem, right? वो challenging हो गया आपके लिए. तो अभी से आप तैयारी पकड़ लें आप अपनी.
ठीक है सर. आप
ओके ओके, वसीम है आपका कोई क्वेश्चन?
नो सर.
अच्छा ठीक है, वी आर डन फॉर टुडे. या
सर आपने मतलब हमने ये पढ़ा है कि ये कोई भी कंटिन्यूस बीम जो है उसके किसी सेक्शन को हम इस तरह एनालाइज कर सकते हैं, तो क्या वो इंडिपेंडेंटली सारे एनालाइज होते हैं इस मेथड के थ्रू, या इफेक्ट होता है एक पोर्शन का दूसरे पोर्शन में?
नहीं, इंडिपेंडेंटली का क्या मतलब है आपका?
सर कहने का मकसद ये है कि देखिए, अगर हम कोई सेक्शन उठाते हैं तो बाकी जो बीम का पोर्शन है उस पर भी तो लोडिंग होगी, तो क्या उसके इफेक्ट आएंगे उस सेक्शन पर या नहीं?
हाँ ना, वो तो ऑलरेडी इंक्लूड हो जाते हैं ना. ये जो हम टू द लेफ्ट और टू द राइट लेते हैं ना, तो एक जगह फर्ज करें आप इंटरनल एक्शन में, फर्ज करें आप इंटरेस्टेड है टू द लेफ्ट, तो फिर करस्पॉन्डिंग जो भी टू द लेफ्ट है वो आप एनालाइज करेंगे, वही वैल्यूज आप उठाएंगी वहां से. इंडिपेंडेंटली तो इस तरह तो नहीं हो सकता ना. पहले जो हम एनालाइज करते हैं, वी टेक देम एज ए फिक्स्ड एंड एक्शन, और सारे स्ट्रक्चर को देख के हम करते हैं. हाँ, अगर एक सेक्शन पे अगर आपको चाहिए कि फर्ज करें आपको ये कहते हैं कि टू द लेफ्ट ऑफ लेट्स से सपोर्ट ए पे आप मालूम कर लें. ठीक है, सपोर्ट ए पे क्या मोमेंट आप मालूम कर लें. यहाँ पे फिक्स सपोर्ट था, तो एक दफा अगर आपके पास है ना, अगर अननोन जॉइंट डिस्प्लेसमेंट्स है आपके पास, तो फिर क्या करें आप, करस्पॉन्डिंग ए पे जो आपके वैल्यूज आ रहे हैं उसी को, बाकी एनालिसिस की आपको जरूरत ही नहीं. आप समझ रही है मैं क्या कह रहा हूं?
सर ये बात रिपीट कर दे, मैं नहीं समझी.
अच्छा चले, यहां पे चले जाते हैं. लेट्स फर्ज करें मैं आपको दे देता हूं कि आप जो है ना मोमेंट एट ए मालूम कर लें. ठीक है, वेयर इज मोमेंट एट ए? लेट्स दिस सिचुएशन आई एम गिविंग यू, दिस AM5 जो है ना यहां पे AM5, करेक्ट?
जी.
अच्छा, let's this is moment at A. I'm asking you that you just give me this value due to any reason, because of the shortage of time, or let's say I'm giving you more work and I'm asking you give me the MA value by applying the stiffness method. अब आप मुझे ये बताएं कि मोमेंट एट ए आप D1 और D2 के बगैर आप मालूम कर सकते हैं? बिल्कुल भी नहीं, क्योंकि स्टिफनेस मेथड हम यूज कर रहे हैं। तो मेरा इंटरेस्ट क्या होगा कि पहले मैं D1 और D2 में यूज करूंगा। अच्छा, D1 और D2 आपके मालूम हो गए, तो उसके बाद क्या करते हैं, हम डायरेक्टली यहाँ पे AM पे आते हैं और इसके करस्पॉन्डिंग वैल्यूज जो है ना वो सिर्फ मुझे चाहिए अब इसको मालूम करने के लिए। आई डोंट नीड दिस AM1, AM2, AM3 एंड AM7 दीज थिंग्स। इसी तरह अगर जॉइंट डिस्प्लेसमेंट में हम चले जाएं, लेट्स से हियर S11, S21, इसको आप देख लें, लेट्स D1 एंड D2। अब D1 और D2 मालूम करने के लिए मुझे क्या चाहिए, यही ADL1 और ADL2 चाहिए। आई डोंट नीड दिस PL और दिस, ये चीजें मुझे नहीं चाहिए। इसी तरह if I go to the stiffness coefficient, then I need only this one for the S11 and this for the S21. So I need only these values. I don't need to go through all these values. Similarly, for the second column, I need only this value and this value. I don't need these support reactions. So based on your need, you will have to find out those member indexes and then you run the matrix, this जो calculations है उसको आप run कर लें।
ठीक है सर।
ये तो मैं डिटेल में कर रहा था ना। अब इसमें मैं ये भी कर सकता था कि लेट्स से यू गिव मी द सपोर्ट रिएक्शन हियर, यहाँ पे जो आपका मोमेंट आ रहा है ना 30 के, let's say that is becoming your unknown moment now, वो भी आप इस मैट्रिक्स मेथड से वही करस्पॉन्डिंग वैल्यूज आप लेंगे वहां से और ये चीजें आप कैलकुलेट करेंगे फिर इसी तरह 20 पे। लेकिन वो कॉम्प्लिकेटेड हो जाएगा बड़ा। कहाँ पे कॉम्प्लिकेटेड होगा, लेट्स से इसके करस्पॉन्डिंग वैल्यूज अब यहाँ से हम कैसे मालूम करेंगे, इसके करस्पॉन्डिंग वैल्यूज यहाँ से जब मालूम करेंगे बड़ा मुश्किल हो जाएगा। इसके करस्पॉन्डिंग वैल्यूज यहाँ पे मालूम करेंगे तो बड़ा मुश्किल हो जाएगा। That is why I am ignoring those sections now to make my life easier. Any question? ये देखिए ये बड़ा आसान हो गया ना। यहाँ से जब सपोर्ट रिएक्शंस हम करते हैं, लेट्स आई सपोर्ट रिएक्शंस कहाँ से आ रहे थे, मैं सपोर्ट रिएक्शंस में था तो उसकी करस्पॉन्डिंग वैल्यूज मैंने उठा दी। फिर जब मेंबर इलेक्शंस पे आ गया तो उसकी करस्पॉन्डिंग वैल्यूज मैंने उठा दी। एनी अदर क्वेश्चन?
जी सही है सर, क्लियर।
अच्छा, we'll be solving 2 more problems, so if you have any question then you can ask me there. Okay, so with this now we are done for today and I'll see you inshallah coming Monday, which will be 28th, I think, yeah, which will be 28th of December. Okay, thank you so much.